All right, next up is question 6, which is another work calculation. And it says that the force exerted by an electric charge at the origin on a charged particle at a point xyz with position vector r, which is equal to xi plus yj plus zk, is given by this field E, which is equal to k times that position vector divided by the scalar r cubed. Now here k is just a positive constant and r is just the distance from this point to the origin, right? So we saw this in section 15.1. This right here is really telling us that this electric charge obeys an inverse square law. Okay, so our job is to find the work done as the particle moves along a straight line from the point 200 to the point 215. And then it says explain the sign of your answer. Okay, so much like what we did in question 5, we'll start by parameterizing our path. And for that, I'm just parameterizing a straight line segment. So to do that, let's go ahead and just take this direction vector that runs from the point 200 to the point 215. Okay, so if I call that direction vector, say v, its components are found by just subtracting coordinate-wise. So I'll do 2 minus 2 would be 0, 1 minus 0 would be 1, and 5 minus 0 would be 5. Okay, so then to write down parameterization for this segment, okay, we're going to just take our starting point, 200, and add to it t times this direction vector v, which is 0, 1, 5. Okay, so this is some Calc 3 coming into play, and I'll go ahead and just combine all that as a single vector. So this is going to just be 2 because I'm going to get a 0t there. So just get a 2 here, and then 0 plus t would just be t, and then 0 plus 5t would be 5t. Okay, so that's a parameterization for the path. And here, t will vary from just 0 to 1, right? T equals 0. We're going to be at this point 200, and then t equal to 1, we're going to be at this point 215. Okay, great. So now here is our electric charge, and it's k times this position vector r divided by that scalar r cubed. So if I write this out in terms of x, y, and z, this would be k over, if I cube this scalar r quantity, that's going to give us x squared plus y squared plus z squared to the 3/2 power. And then the position vector xi plus yj plus zk, I'll just write in angle bracket notation. It's just x, y, z. Okay, cool. So now to compute the work done by this electric charge in moving this charged particle from the point 200 to 215, we're going to compute the line integral of our field over this path. And to compute that, we're going to take the integral, as we let t vary from 0 to 1, of our field evaluated along the path, dotted with the derivative vector. All right, so let's go ahead and unpack each part of this integrand. So I need to evaluate the field E along the path. And so to write down an expression for that, I'm going to have k over, and now along the path, x is equal to 2, y is equal to t, and z is equal to 5t. So I'm going to go ahead and plug in 2 for x, and I'm going to get 4 there when I square, then plus plugging in t for y, t squared, and then plugging in 5t for z, I'm going to get 25 t squared. and then that's to the 3/2 power. And then our components here for this vector x, y, z would then just be 2t, 5t, when I just substitute in 2 for x, t for y, and 5t for z. All right, now we can clean this expression up downstairs a little bit, so we'll go ahead and do that. Get 4 plus 26t squared to the 3/2, and then we have our 2t, 5t. All right, so that is this portion here, the e of r of t. Now what about the derivative vector? Well, that's actually just this direction vector, right? Because when I differentiate, it's just going to give me this vector tangent to our straight line path. So differentiating, I'm just going to get 0, 1, 5. Okay, great. So now let's go ahead and set this up. Got 0, 1. I'll go ahead and punch in this e of rt expression here. So 4 plus 26t squared to the 3/2. And then we have this vector 2t, 5t. Then we're going to dot that with r prime, which is just 0, 1, 5. And then we're going to integrate that resulting expression with respect to t from 0 to 1. All right, so I'll go ahead and pull the k out in front. And for the dot product, okay, I'm going to get, well, 2 times 0 is 0. I'm going to get t times 1 is t, and 5t times 5 is 25t. Okay, so if I just look at this portion right here, all together, I'll wind up getting just 26t. Okay, so I'm going to get a 26t, and then that's going to be divided by this expression down here, the 4 plus the 26t squared to the 3/2. All right, now this is starting to look a little nicer. This is an integral we can compute with just a substitution. So I'll let u equal that inside 4 plus 26t squared, and du can be 52 then t dt. So we go ahead and substitute. What are we going to get? We're going to get the integral. If I let t equal 0, I'm going to get 4. And then setting t to 1, I'm going to get 30. And 26t dt, well, that if I just take half, if I take a factor of 2 and divide, I'm going to get just du over 2. And then down here, I'm just going to get u to the 3/2. Okay, now that's a nice computable integral. So we'll get k times, and the antiderivative here of 1 over u to the 3/2, this is going to be minus 2 over the root of u. And, and sorry, and I had that factor of 1/2 there, so I'll pull that in front. And then we're evaluating from 4 to 30. There we go. And so these 2's are going to drop out. And then when I evaluate, I'll get minus 1 over the root of 30 minus a minus, so plus 1 over the root of 4, and that's just going to be 2. And I'll go ahead and write the final answer there just to really highlight the fact that this is a positive quantity, is 1/2 minus 1 over root 30. Okay, so this is a positive value. And so as far as explaining the sign of this answer, well, our electric charge field here, right, it is a radial field, right? So in other words, it's pointing directly outwards. So if I'm it's pointing directly outwards from the origin, right? So if I'm moving a particle from, say, a point 200 to the point 215, I'm moving further away from the origin. So it makes sense that this electric charge here is going to be reinforcing that direction of motion. Okay, so yeah, that makes sense that this would come out to be a positive work. And that'll do it. Thanks so much.